Now, if you can do one mapping, like if you can map from this to this, how about a second mapping from this to another one, also set A? So, so that would be like mapping F, and the next one would be like mapping G. Okay? So you can combine permutations. You can do one after the other, and that's equivalent to composition of functions. Right? We did a whole lecture about that. You know, like FG, or rather GF. You apply function F first, get the result, and then apply function G to it. Right? So we can do something similar here. So putting two permutations one after the other is equivalent to just composing or putting together, like followed by two functions. You know, one function followed by another. Okay, let's do a concrete example here. Here's one permutation, right? And here's another one. Now, in the first permutation, one maps to itself, doesn't change, and similarly for 2. But 3 gets changed to 4, and 4 gets changed to 3. That's permutation 1, right? So effectively, you've swapped objects 3 and 4. And then to the result, and this is the result. This is what you start with. That's the order, the ordering, if you like, that you start with, and that's what you end with. So the start, end, and then you to this becomes your starting point for a second permutation. And here's the second permutation. It takes 1 and maps it to 3, and 2 maps to 2, 3 to 4, 4 to 1. Right. So let's find the result of doing 2 permutations, and the result will also be a permutation, because you know, all this mapping is 1 to 1. So the result of doing 2 permutations is yet another permutation. Right? In that sense, it's closed. All right. So this is how you do it. Now we'll do this one first, then we'll do this one. Okay. So 1 maps to 1, and then you apply the second one. So the result is 1, but that becomes the new starting point here. And then this 1 maps to 3. So 1 maps to 1, that's your first part of your first permutation. And then in the second permutation, 1 to 3, 1 to 3. So the net effect is that 1 maps to 3. Okay? So 1 maps to 3. That's the result of doing 2 permutations. Okay? Now 2 maps to 2, and then 2 maps to 2, no change. Okay? 2 to 2 to 2, so 2 to 2. This is the result permutation. And 3 maps to 4, 3 maps to 4, and then 4 maps to 1. 3 goes to 4, 4 to 1. So the result is from 3 to 1. 3 to 1. Right? Now in the first permutation, 4 maps to 3, and then 3 maps to 4. 4 goes to 3 to 4. So 4 goes to 4. 4 goes to 4. Right? So it seems. Now a little later we'll do a slightly more complicated example of that, in a sense, in a manner of speaking, multiplying 2 permutations, or in other words, applying one after the other. You know, I'll actually do some here in a couple of minutes, but do you notice something? We seem here to have 2 different notations. Like we have this bracket notation, right? Bracket notation, like this, right? That's the starting configuration, and that's the ending configuration. So the combination is a permutation. You've changed the order. This is the old order, that's the new order, if you like. Okay? So what are the pros and cons of the 2 notations? The other one being, of course, the mapping, the function notation. Okay? So the function notation or the bracket notation. Now the 2 are equivalent, right? It's fairly obvious, I assume. Okay? Now if you express a permutation in terms of a function and sets, this is pretty bulky, right? takes up quite a bit of space on the board, on the printed page in your textbook or whatever. Okay, so the advantage of the bracket notation, mention it here, is that less space is used. Okay, so that's one of the plus points. And so this bracket notation tends to get used quite a lot. Now, in fact, in a later session of this lecture, I will use a third notation. I'll take the bracket notation and simplify it. Well, I'll just mention the keyword cycle. I'm getting a bit ahead of myself, but so there is a third notation, right? It's a special case of the bracket notation using so-called cycles. Okay. Now we can get our first solid result. Now I hinted a bit earlier that the set of these permutations, like if you have three objects, how many ways can you permute those three objects? Well, if you started with a red here, how many different colours could you put here? Well, you've got three choices, right? That leaves two rings to use, and then so how many could you put here? Well, you have two choices, so you have 6 choices altogether. That only leaves one. You can only put that remaining ring there in one way, so it's 3 by 2 by 1. Okay. Now, in general, if you have n, like n poles, n rings, n objects, the number of permutations will be n factorial. I hope that's fairly obvious. Okay. Now, theorem 34. I'll read it out because we don't have to go through all the rigmarole of proving that the set of permutations. Well, I need the page number. Just going to even earlier chapter. Yes, it is. Right. Page 86 in your textbook, and I'll just read it out. So the set of bijections from a set A to itself, so A to A, okay, together with the operation of composition, just in other words, followed by, okay, is a group. Okay. Now, what do we have here? We have bijections. We have a bijection, right, from this set to this set with this function f. And so the set of all these functions, all these bijections, all possible, and how many are there? N factorial. Right? They're all bijections. They're all mappings from the set A to set A. Okay? And the binary operator, if you like, is just followed by, do F, then do G kind of thing. Right? So we can use theorem 34 to conclude immediately that this set here, which is the set of all permutations of your n objects, right? With this binary operator, which is just composition of functions, which is the fancy way of saying followed by. You do this, map this f, followed by mapping g, whatever. Okay? So this duo, because remember a group is always a set and a binary operator. You need both. Okay. So this set of all permutations, n factorial of them, and the binary operator is just followed by. That is a group. Okay. So the set of permutations with this binary operator is a group. So we can talk about the group of permutations. All right. Okay. Now this particular group is so common and pretty famous in group theory that it has its own symbol and its own name. In fact, as I was mentioning a bit before, okay? So here's your set. Let's just say the first n, so n objects, first n integers and you can give each object, whatever it is, like coloured marbles, people, whatever, you can give them a numerical, an integer ID, identifier. Okay? So if you have n objects, your binary operator is just followed by, you perform this permutation followed by another permutation. This set goes under the name, well, it's a group, right?